All right, so we're gonna do the Livin on the edge linearization formative, and I haven't done this before. And if you haven't done this before, you should pause and do it, and then come back and see if you messed up, where you could improve, or mistakes and whatnot. I might make mistakes. We'll see. Living on the edge. That's a fun name. Living on the edge. Okay. So you can go ahead and read this. I'm just gonna kind of pick some key points out here. I haven't read it, to be honest, and I'm gonna do the thing that you really shouldn't do. If you're on a test, you shouldn't do what I'm about to do, but we're just gonna roll with it. Pendulum and peg lab for summative, and there's going to be a mass M that's going to be swinging in kind of instead of a lower bar. Oh, okay, so basically you're going to have a pendulum, and you're going to have, instead of a peg, there's going to be a knife, so that it essentially makes it move into a projectile. And the height of the mass at its lowest point, this is H, this is L, the length of the string, and then it starts at an angle theta. And they're measuring the change in X. And my guess is, so the angle theta is varied. So this angle theta is varied. So let's find a relationship between theta and the change in X. So we know that the change in X, because it's going to be moving in a constant velocity, and the X component of its velocity is not changing, it's going to be Vx times time. That's the change in X. To find time, I would use the kinematics equation, H equals 1/2 AT squared, right? All of this in the V direction, V naught times time. I know this is 0, and then I would just do 2H over G is equal to T, and then I can take the square root. I would get square root 2H over G. Now, as for Vx, I could use energy for that. So the energy in this case, right, at the very top of its swing, or the highest point that it starts, really you would have UG initial equals K plus UG final. What you can really do is you can kind of say, okay, this at this point, you can either say there's no UG, but I think the better way to do this, if you want to conceptually understand this, is you could say there UG you could say the UG is 0 here, right? So there's going to be some UG at point B, and there's going to be more UG at point A. And what I get is I'm going to have MGH1 is going to equal K plus MGH2, right? So I'm going to have, if I subtract over this term, I'm going to have MGH1 minus H2 equals K, right? So this is really MG change in H. So that's what I'm trying to show here, is that really it's the change in height that we want to kind of figure out. And that's why what we're going to do is we're going to say, okay, this is going to be part of a circle. So this length right here is L. And I'm trying to find this change in height, right? It's changing its height from this point down to there. So if the total length here, right, if the total length is L, this length right here using trigonometry would be L minus L, I kind of gave it away, but this would be L cosine theta, so I subtract the two. The change in height is going to be L minus L cosine theta. So G times L minus L cosine theta is going to equal 1/2 V squared once I drop the M's. So 2G L 1 minus cosine theta is going to equal V squared. Take the square root, and then I'm going to multiply it by the time. So the total change in X is going to equal the speed, which we just derived as 2GL 1 minus cosine theta, times the height, that was 2H over G. And I can put this all in the same radical. That's how algebra works. And I would get 4LH 1 minus cosine theta. So when I'm graphing this, I have change in X squared is going to equal 4LH minus 4LH cosine theta. And this is, you're going to see, I'm going to want to graph cosine theta versus change in x squared. That's how I can linearize this. Slope is going to be negative 4LH, so it's going to be, there we go, negative 4LH. And the y-intercept is going to be positive 4LH, just based off our derivation. Please don't tell me they gave us data. Oh, they don't. That's awesome. So I can just plow through this. X-intercept, what does it represent conceptually? So the x-intercept is when, hey, I'm varying cosine theta and this is change in x. Well, I'm looking, x-intercept is when, right, if I have, the graph's gonna look more like this. But the x-intercept is when cosine theta is equal to 0. That's when theta is equal to 90 degrees. So, hey, that's like if I was launching it completely, like, at a right angle, and then the razor cuts it like so. So this, this point indicates when the string was launched, when the string was vertical, so that's not it. This point represents the maximum range. Or is it talking about this? Is it talking about the x-intercept, like? No, because this is the x squared intercept. Okay, we're just going to keep going then. This point represents the maximum range of the mass, which is equal to 4L. Wait. I'm so silly. Wait, what? Cosine theta is the x variable. And the change in x is measured. So I'm gonna say this. Wait, this is no, but that doesn't make sense. Cause like I don't remember what is that even talking about. Let's do y-intercept first. Why not? Let's just do y-intercept. So this point represents. Oh, maybe. I want to say this is the maximum range. All right, we're just going to keep going without wasting too much time. What does the y-intercept represent conceptually? And I'll come back to that question. But this, I would say, oh, that's when the change in x is equal to 0. I'm so silly. The x-intercept is when the change in x is equal to 0, because that's when it crosses. So this would be 0.3. This is like when the string was not even raised, right? This would be cosine 0, right? That would equal 1, so I get 4LH or minus 4LH, which equals 0. So this is like when I don't even pull it back. This is when the string is completely vertical. This is the maximum range, right? Because the y-intercept is 4LH, so this would be 2 root LH is the max range. And this is also when it's launched from horizontal position. Is it point? Yeah, I'm pretty sure it's just those two. And we're gonna see how the linearizations change if you were on the moon, Mercury, whatever. And actually, what's beautiful about this is nothing would change. You would get the exact same graph. And the reason is because when you change a gravitational, thing, right? When you change a gravitational field strength, your speed changes by a certain amount. Like, let's say it decrease. Like, if you go on, I'm not gonna do the actual. Okay, we can do. like if you, let's say, let's do the actual linear or the actual proportional reasoning. If I go I don't really want to, but it's fine. Mg like L minus L cosine theta equals 1/2 mv squared. If my gravitational field strength is like 1/9 as much, you would get 3 times this, or wait, that makes, oh, you would get 1/3 the speed, right? With your proportional reasoning, when you square that, you get 1/9, and then both sides are balanced. You get 1/3 the speed, but you would get 3 times the time in the air, because, right, if I put 1/9 here, I would get 3 times the time. So it's like, it balances out pretty beautifully. So yeah, that's that. We're going to see if I got all my correct answers. 3 out of 3, please. It's going to be really embarrassing if I don't. Okay, there we go. Thank you for